The electromagnetic spectrum. There are a few things you need to know about this. Here we have a scale of both wavelength and frequency. We don't need to worry too much about what this one is down here, but within this we've got some things to let you see the sizes we're talking about. So the electromagnetic spectrum is a bunch of waves that are coming from the sun. The important thing about these waves, one of the important things about these waves, is that this is a continuous spectrum. That is to say, where we have divided up radio waves and microwaves and visible light and so on, we've made those divisions artificially. We've said this little bit is radio waves because we use them in that particular way, and this little bit is microwaves and so on. But you have this continuous stream of waves coming from the sun. Now, these are a special set of waves in the sense that they are the only waves that travel at the speed of light. They are the only waves that can travel in a vacuum. So they're the only waves that don't need something to travel through. Sound waves need some kind of material or medium to travel through. Without them, in a vacuum, there is no sound. Whereas these waves can travel through a vacuum. And of course, we know they can because we know that there is a vacuum between the sun and the earth, and yet we get heat and light, and indeed all of these waves from the sun. So they must be able to travel through a vacuum. So this gives you an idea of the scale of things. When you're looking at 10 to the 2, that's 100 meters. You're talking about a football field. You're talking about tens of meters. You're talking about the dimensions of a house. The width, the depth, the height of the house is in tens of meters. A tennis ball or a baseball, you're looking at centimeters, 10 to the minus 1. Tens of centimeters. A millimeter, well, this is a full stop. This is an American slide, so it's called a period, but this full stop is about a millimeter across. And then you're into cells and bacteria at millionths of a meter, microns. Smaller than that, a tenth of that size is the virus, and so on. So you get an idea of the size of these things. Radio waves are up here. We call them in here, in the centimeter range, we call them microwaves. And then we have infrared, visible, ultraviolet in here. Now the visible section is in here, it's very, very small. And then going this way, we've got X-rays and gamma rays. So we have this continuous spectrum, that is to say, one runs into the next. Radio waves are long wavelength microwaves, microwaves are long wavelength infrared, and so on. So you have this continuous spectrum. We have divided them up into these because radio waves do things that microwaves don't do, microwaves do things that infrared doesn't do, and so on. So we have divided this up artificially, but you have this continuous stream of waves coming in from the sun through space, and within that you have these different waves that we can use for different things. So what do you need to know? Well, you need to know the names of them. So you need to be able to say radio, microwaves, infrared, visible, ultraviolet, X-rays, gamma rays. You need to know those names. You need to know the order of them, that radio waves are the long wavelength, and then you've got microwaves, infrared, visible, ultraviolet, X-rays, gamma rays. You need to know the order of them. You need to know the uses, some of which you know already, and some of which I am going to introduce you to today. So you need to be able to say for each of these a use of them, and you need to know where they're dangerous or which ones are dangerous. So we'll look at that. So the names of them, the order of them, the approximate wavelengths. Excuse this. So the approximate wavelength of them or the frequency of them, and there's a pattern to the wavelengths to help you with that. Uses, dangers, and the special properties that I talked about a moment or two ago. That is to say, they all travel at the speed of light, which no other wave can do. They all travel through a vacuum. Strictly speaking, that's one special property, but generally is treated as two. They travel at the speed of light in a vacuum. They are the only waves that travel at the speed of light. They are the only waves that travel in a vacuum. So you have this document, and I have pre-filled. There's a word missing here for you. What kind of spectrum is it that are all coming from the sun? And we divide up into sections. The two special properties that I mentioned a moment or two ago. Then you have the names of them in order, and you have the wavelengths here. Now, wavelengths, there's a pattern to them. You can see that radio waves are in the sort of meters to kilometers range, 1 to the thousands. So around 100 would be a typical wavelength. Microwaves, centimeters, 10 to the minus 2 meters. Infrared, 100 times smaller than that. Visible, well, visible is very tightly defined as between 400 and 700 billionths of a meter, 10 to the minus 9 nanometers. Now, that's because that's what we can see. That's what our eyes are sensitive to, that very narrow range. So that's about 100 times typically smaller than this. This is 4 times 10 to the minus 7. This is 7 times 10 to the minus 7. So around 10 to the minus 6. Top end of 10 to the minus 6 here. So 10 to the minus 2, 10 to the minus 4, 10 to the minus 6, 10 to the minus 7, 10 to the minus 8, 10 to the minus 10, 10 to the minus 12. So there's a pattern in there. A factor of 100 between them pretty much. Radio waves, meters, you could say that's tens of meters, 10 to the 1, 10 to the minus 2, 10 to the minus 4, 10 to the minus 6, 10 to the minus 8, 10 to the minus 10, 10 to the minus 12. So there is a pattern there for you. As we go through here, I'll talk about uses, dangers, and you can fill this in. I'll be looking to see that you fill this in as we go. Okay, so you know the names, you know the order, you know the approximate wavelength, you know the special properties, you know that they are continuous spectrum. Those are things that if they aren't in that document already, you can put in now. So, looking at radio waves. Now, I'm going to look at this from the context of medical physics mostly, but I am going to throw in some other uses for you as well. So, mobile phones, you'll know all about mobile phones being supposedly dangerous. And the reason that mobile phones are supposedly dangerous is because they emit microwaves, and microwaves are absorbed by water. That's how microwave ovens work. The water in the food absorbs the microwaves, gains more energy as a consequence. They vibrate faster, and so the food gets hotter. But we are mostly water, and so the water in our brains absorbs the microwaves and gets a bit hotter. So here you have some thermographs, some pictures looking at the infrared coming off the head, and you can see that this bit where the phone's transmitter will have been next to the ear is hotter than this bit, which is hotter than this bit. So you may think, oh no, I'm heating my brain, that's a bad thing. Look at the temperature scale here. So you're looking at a 0.2 degree difference between here and here. So it's not a big temperature difference. The question then for the medics is that dangerous? Well, the evidence seems to be that it's not. The jury's still out a little bit, but the more evidence we get, the less we think it is dangerous. So radio waves are also used therapeutically. Longer wavelength radio waves than microwaves can be used therapeutically. They can be used to help with muscle injuries. But obviously we use radio waves for communication. It's radio that we use for terrestrial television. It's radio we use for radios, audio programs on radio. So we use radio waves for communication. We use radio waves for Bluetooth. So infrared then. Infrared we can use to look at brain activity. So what we have here is a baby wearing a hat, and inside the hat there are lots of infrared detectors, and when the baby looks at the changing pattern on the computer screen, the detectors detect the changes in temperature and therefore the changes in the infrared in the brain, and so they can work out which bits of the brain are working. So we can look at brain function using infrared. We also, of course, use infrared for cooking. The grill in your oven uses infrared. We give out infrared. Every warm object gives out infrared. We use infrared for television remote controls, for example. It might be that if you take the camera on your mobile phone and you point it at the end of the remote control and you press a button on the remote, you might be able to see the little LED on the end of the remote flashing. Although you can't see it with the naked eye, it happens that your camera may be sensitive to that near infrared, and so you can see it flashing with the camera where you can't see it with your eye. That's infrared. So infrared is used in the home for cooking, with the grill, for example. It is used for remote controls. It's used for thermal imaging cameras. Let me give you an example of that. Here we have a helicopter with an infrared camera looking for a criminal. Judging by the title of this, they were looking for someone who planted a bomb in Boston in the States. And with the naked eye, you wouldn't be able to see this guy hiding underneath the tarpaulin inside this boat. But here he is. There's his head, there's an arm, there's legs. He's got himself next to some kind of container on the deck of the boat here. And the police camera can see him clear as day in that boat. Now, of course, they might not know that it's him, but they know there's someone in that boat, and they would go and check it out. So infrared cameras used to find people in earthquakes, for example. If they're buried, they can use the infrared cameras to find them. Infrared cameras used for security. So if you're approaching a military installation somewhere, there'll be infrared cameras around the fence so that even when it's pitch black, they're able to pick you up. They're used for police chasing stolen cars, criminals generally. They can tell whether the car has just been driven, so maybe a drunk driver might come home before the police get to them and say, oh no, I haven't been out, and the police can put a thermal imaging camera on the car and say that car's been driven recently. So maybe you have been out. Anyway, thermal imaging cameras use infrared. Here we have a premature baby, and obviously premature babies need an awful lot of support. You can see lots of tubes and wires here. One of the things that they can do with the baby when they are being born is they can check the uptake of oxygen of the blood using infrared. So here you have the hemoglobin, which hopefully you know is what the blood uses, the red blood cells use to carry oxygen. Here you have oxygenated hemoglobin, when the hemoglobin has picked up the oxygen. So they can use this to trace the uptake of oxygen in the blood. So they don't have to wait to see whether the baby stops being blue or becomes blue to know that there's an oxygen deficiency. They can measure it and act quicker so that the baby's less likely to suffer harm. And this is actually as the baby is being born. So the baby hasn't quite been born here, it's just about to emerge. Here the head has been delivered, and at the point where the head comes out, shortly after that, the baby starts to breathe, and you see the oxygen uptake there. That's what you're expecting to see, and if it doesn't happen, they can detect that quickly. Pulse oximeter. This is a great device, which again uses infrared. You've seen these things, maybe even had one of these used with you. Infrared is emitted here, passes through the finger and detected here, and there are two things that this will do. It will pick up the pulse, because as the blood pulses through the finger, the amount of infrared that's being detected falls, and it can also work out the level of oxygen in the blood. So you don't have to take blood and look and see how much oxygen is in there. This will tell the doctors and nurses pretty much instantly the level of oxygen in the blood. And there you can see 98% oxygen, heart rate 80 beats per minute. So that's pretty good. So that's infrared. Thermal imaging again, we talked about it in terms of security and in terms of disaster recovery and that sort of thing. Here we have it medically. You can see warm fingers, but you can see here these fingers are cold. Now that might be because there's a poor blood supply to those fingers, and indeed you can see this part of the hand over here doesn't have the same blood supply as up here. You can actually see in this arm, you can see the veins. So you can see quite easily the blood supply, and you can see where there may be a problem with the blood supply. And clearly, if there's a long-term problem with the blood supply here, you know, if we had an injury to the hand and the blood supply is not getting to the fingers, these fingers are in danger of being lost. The flesh will die without the blood supply to keep it alive, so you could lose your fingers. And so here's a nice, quick, easy way of checking that and taking action based on what the doctors, nurses see. And here we have an ordinary image, an ordinary picture with the thermograph overlaid, so you can see more clearly where the cold areas and the hot areas are. These triangles are to allow them to match up the two photographs. And you can see, if you look carefully, you can see they haven't quite matched them perfectly. But that allows you to see the warm and cold and really quite cold areas. We don't have a scale here, but the back of the arm is significantly colder than the middle of the back, which, you know, you would expect. So, visible light then. Well, one of the ways we use visible light is looking at the back of the eye. Of course, we use visible light to see stuff. And visible light, like radio waves, like microwaves, it's not dangerous except it's in high intensity. So if this was a laser pointer, for example, some laser pointers are quite dangerous and they will damage the retina before your eye can react and close the pupil down to protect itself. So high intensity light, high intensity microwaves, high intensity radio waves are dangerous. Microwaves from phones are not dangerous, except if you were to climb up a mobile phone mast and stick your head in front of the transmitter, that would be dangerous because there's an awful lot of microwaves there, a high intensity of microwaves. So microwave ovens are dangerous. You should not climb inside and turn them on because that's high intensity microwaves. But the microwaves, the radio waves that are around you all day, every day due to mobile phones and television and radio broadcasts, they're not dangerous. Likewise with light. Very bright light will damage your eyes. A very intense light will damage your eyes. But everyday uses are safe. Also using light, endoscopes. You may have seen these. Possibly in hospital programs, you may even have had an investigation using one. But this is what allows keyhole surgery. So you have, on the end of your endoscope, you have light, you have tools, you have a water supply, you have air So you can get light and tools into a very small area by making a small incision, or even just going down the throat. Now you might say, putting that down my throat does not sound pleasant, and indeed it's not. But the alternative, of course, if you have some kind of gastric problem, here we have the esophagus and the stomach. Now this allows us to see the hernia where the stomach wall has fallen into the esophagus. And here we can see a parasite. Now these are things that you wouldn't be able to detect anything like as easily without the endoscope. So it avoids major surgery, it avoids surgery at all sometimes. So it's a good thing. But there's other ways of doing this. This is a camera pill. So this is, again, looking inside, endoscopy, and inside, scopy, looking. So we're looking inside with a camera pill. So this is a pill that the patient swallows, and it sends back signals that the doctors can watch. And here you have an X-ray showing the camera pill inside, and some other wires as well. So they can follow the path, they can look at the digestive tract using this camera, and all you've had to do is swallow the pill. No great endoscopy tube. Or they can go a step further. We'll look at CT scans in a minute or two, but they can take a 3D X-ray, which is a CT scan, and then they can use a computer to build up a picture, and they can actually get a virtual tour inside the body. So by using the CT scan, they can actually look inside the body and see what it looks like without actually going inside. And they can perform surgery. Here we have a laser which is destroying some cancerous growth. And the laser will not only destroy it, but it will also seal up the bleeding. So you don't need stitches. And again, imagine the alternative here is to have surgery where they open you up and they cut out the tumour, and then they'd have to close that up. Maybe they would use a hot wire essentially to seal it up the way the laser's doing. Maybe they would use dissolvable stitches. But the point is that it would require surgery. Whereas with the endoscopy, they can do it all by going in this case, by going in through your esophagus. But maybe elsewhere they would make a small incision to get at this, rather than having to open you up in a more major way, which means you recover faster, it's less of a risk. So it's a really good thing. You can also use visible light to remove skin blemishes. Treatment of jaundice. Jaundice is the liver's not working properly and there's a build-up of a yellow substance in your skin which turns you slightly yellow, and you can use blue light to destroy, to break down that yellow bilirubin it is in your skin. And so very often newborn babies will have jaundice, and they can use this blue light then to get rid of that yellow compound in the skin. X-rays and gamma rays. Well, here we have the first X-ray picture. This was taken by a guy called Röntgen. This is Röntgen's wife's left hand, and this is her engagement ring. Quite a large diamond there, folks. So Röntgen was not short of a pound or two. So a more modern X-ray, rather clearer. You can see all the bones as clear as day in the hand. Here you have a 3D, a CT scan, a 3D X-ray. And not only is this a 3D X-ray, but it's also computer rendered. So we have the tendon and ligaments and muscles all rendered in here, so we can see them too. And it's 3D. Now that's really important, as you'll see in a minute or two. So X-rays are used to look inside the body. Here we have a CT scan of the pelvis, and you can see a crack in the pelvis. So it's not actually broken, but it is cracked. So that's a serious injury. So X-rays. X-rays are used to look inside the body, but they're also used to kill cancer. You might say, well, hang on, X-rays cause cancer, don't they? Yes, they do. But the way we do this limits the damage to healthy tissue while maximizing the damage to the cancerous tissue. So this patient has been placed so that the tumor, the cancer, is in the middle of the circle that this X-ray machine is going to perform. So this, which produces the X-rays, is going to move in a circle around him. So the X-rays are always being fired at the tumor, and the healthy tissue all around the tumor is getting a smaller dose because the X-ray machine is rotating, but the cancer is always getting a big dose. As it goes round, it's always firing at the cancer. So the healthy tissue gets a smaller dose from the cancer, and also the cancer cells are more susceptible to damage by X-rays, gamma rays. Both are used to kill cancer. So whilst X-rays and gamma rays are dangerous because they cause ionization, they damage cells which can cause cancer, they are used to kill cancer, and this is how it's done. And cancer is basically uncontrolled growth of cells, and cells which are rapidly multiplying, like hair cells, like sperm cells, for example, these are more susceptible to ionizing radiation, X-rays, gamma rays, than other cells, and so the cancer cells take a smaller dose to damage them. So do your hair follicles, and sperm cells, for example. Rapidly growing cells are more easily damaged. So what they do, they take a 3D scan, an X-ray, a CT scan, and that allows them to pinpoint exactly where the tumour is. If you think about taking a 2D X-ray, you can tell that the tumour lies along this line somewhere, but you don't know whether it's here or here or here or here. And for the treatment, it's really important you know exactly where the tumour is. So you take this 3D X-ray, you find out exactly where the tumour is, and then your radiographer, your medical physicist, decides exactly which way to fire the X-rays and where to place the patient, so that the cancer gets the biggest dose as the X-ray machine rotates around them. So, going back to what you need to know: the names, the order, approximate wavelengths, uses, dangers, special properties. If we go back in here, there's your names, there's your wavelengths, you have that pattern, about a factor of 100 between them. This is more 10 to the 7 than 10 to the minus 7 rather than 10 to the minus 6. So radio waves, communication, Bluetooth, only dangerous in high intensity. Microwaves, mobile phones, microwave ovens, communication generally. Dangers, well, they're absorbed by water, so they can cook you if they're in high intensity. Infrared, remote controls, infrared cameras. Danger, well, infrared causes burns. If you stuck your hand under the grill when the grill was on, please don't do that, but if you did, you would be burnt. So infrared in high intensity causes burns. Visible light, well, we see stuff with them. We can use them for phototherapy. We can use it to look at the retina. We can use visible light for all kinds of useful things. Danger, well, very intense light will damage your retina, so laser pens, for example. Ultraviolet, well, I didn't show you one of my pictures that I had for you, so let me show you that. Ultraviolet is used for forgery detection. So here we have a passport underneath an ultraviolet lamp. Mercury, if you pass a current through it, mercury vapor gives off ultraviolet, and you can also have ultraviolet LEDs. And what you're expecting to see is when the UV hits the passport, it fluoresces, it gives off light. If it doesn't, it's a fake. Same thing happens with banknotes. Banknotes have got dyes in them in certain places that when they're hit with UV, they fluoresce, they give off light. That's hard to forge, and so one of the ways they check high value notes generally, forgers will make £50 notes, not £5 notes, because they're more valuable. So they will check £50 notes by putting them under a UV lamp at the checkout, and they will look to see that the dye fluoresces in the right places. So UV is used for forgery detection. It's dangerous, of course, because it causes skin cancer, only skin cancer. So make sure when you're talking about dangers here, it is skin cancer, not cancer generally. X-rays, gamma rays cause all kinds of cancers. They are used in diagnosis. You can use X-rays to look inside the body and see broken bones and that sort of thing. You can also use X-rays to look at soft tissue injuries. They use X-rays when they're looking for breast cancer, for example, but they use a different wavelength of X-rays which are absorbed by soft tissue, which of course makes them more dangerous. But they use X-rays to detect tumours in soft tissue. They use them to detect breaks in bones. They can use gamma rays. When we come to radioactivity, we'll look at that. They can use gamma rays to diagnose problems, and both X-rays and gamma rays are used to kill cancer. Danger, they cause cancer. So there you have your table of properties, uses, dangers, the two special properties I talked about at the start, and that missing word in what kind of spectrum it is.